This video is over Chapter 32 on the integral test. Chapter 32 will be done in two videos. This is kind of a long chapter, so I'm going to break this up into two videos. Example 202 is to use the integral test to show that the harmonic series diverges. So, to apply the integral test to this series, we calculate this improper integral. Remember, this by definition is the limit as t tends to infinity of the integral 1 to t 1 divided by x dx. This is the limit as t tends to infinity of natural log of absolute value of x evaluated at 1 and t. This is the limit as t tends to infinity of natural log of t minus natural log of 1. As t tends to infinity, natural log of t tends to infinity, and natural log of 1 is 0. So this improper integral diverges to infinity. Therefore, this series diverges by the integral test. The next example is example 203. We're going to test the series n equal 1 to infinity, 1 divided by n squared. We'll apply the integral test to this series. That means we'll calculate the improper integral 1 to infinity, 1 divided by x squared dx. Remember what an improper integral is. This is the limit as t tends to infinity of the integral 1 to t of 1 divided by x squared dx. This is the limit as t tends to infinity of the antiderivative of 1 over x squared is negative 1 divided by x. We're evaluating this term at t and at 1. This is the limit as t tends to infinity. We will substitute t, negative 1 divided by t, minus what we get when we substitute 1, which is negative 1. As t tends to infinity, 1 divided by t tends to 0, so this limit is 0. Subtracting a negative 1 means that this limit is equal to 1. So this series converges by the integral test. Converges by the integral test. So a series can converge by the integral test, and it can also diverge by the integral test, which is what we saw in the previous example. Recall, before we were on spring break, that this improper integral, the integral 1 to infinity of 1 over x to the p dx, converges if and only if p is greater than 1. So that means, by the integral test, that this series, and this is called a p-series, that was a previous definition that's in your notes, that this p-series converges if and only if p is greater than 1. And so we're going to use this corollary to test this series. Now this is not a p-series, it's not a geometric series, but what we're going to do is we'll compare this series to a p-series. The square root of n divided by n squared plus 2n plus 5 is less than or equal to the square root of n divided by n squared, which is 1 divided by n to the 3/2 power. This is a 3/2. Now, the series since this converges, because it's a convergent p-series, it's a p-series with p equal to 3/2, which is greater than 1, then the series that we were given, and in the interest of time, I will just say the given series converges by the comparison test. Okay. Now, what I want to do in the remainder of the video is explain the integral test. So I want to show you why the integral test works. So let's suppose we have our continuous function, continuous decreasing function, such the limit as x goes to infinity of f of x is 0. Here's 1. Now what we'll do is we're going to look at the terms of our sequence. X sub 2 corresponds to f of x sub 2, or f of 2. So this is our x sub 2. So this rectangle has width 1 and height x sub 2. So it has area x sub 2. This rectangle here has width 1 and height x sub 3, so it has area x sub 3. Likewise, this rectangle has area x sub 4, this rectangle has area x sub 5, etc., etc. And so what we have from this is that the sum of n equal 1 to infinity of x sub n is x sub 1 plus the sum n equal 2 to infinity of x sub n. But this is less than or equal to x sub 1 plus the integral 1 to infinity of f of x dx. And so if this integral converges, then the series also converges because it is dominated by x sub 1 plus the integral 1 to infinity of f of x. So if your integral converges, your series converges. The integral test actually said this was an if and only if. And so that means if the series converges, the integral does as well. So what we do with that is we don't look at the rectangles here. Instead of taking these corners, the right corners for the height, we'll take the left corners for the height. And so for the other direction of the proof, we use the same picture, essentially, we just label it a little bit differently. So now we take oops, that is not what we do. Apologies. We take the left corner as the height of our rectangle. This f of 1 is x sub 1. So this rectangle has height x sub 1 and width 1. This rectangle has height x sub 2 and width 1. So it has area x sub 2. This has area x sub 3. And so the integral 1 to infinity of f of x dx is less than or equal to the sum n equal 1 to infinity of xn. And so if the series converges, the improper integral also converges. This will conclude part 1 of the video.